Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the privacy-safe measurement framework, the system that enables accurate measurement while protecting user privacy in a post-cookie world. We'll cover how Google's Privacy Sandbox, Meta's Conversions API, Apple's SDK network, and other privacy-preserving measurement systems work using differential privacy, secure multi-party computation, and K-Anonymity. Whether you're preparing for a senior engineering interview or building privacy-safe measurement infrastructure, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into the privacy-safe measurement framework, the system that enables accurate measurement while protecting user privacy in a post-cookie world. If you have ever wondered how Google's Privacy Sandbox, Meta's Conversions API, Apple's SDK network, and other privacy-preserving measurement systems work, this video is for you. We'll walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in a senior system design interview. Whether you are preparing for a FANG interview or building privacy-safe measurement infrastructure, let's get into it. Here is the core problem. The digital advertising ecosystem is undergoing a massive privacy transformation. Third-party cookies are being phased out, mobile identifiers are restricted, and regulations like GDPR and CCPA require explicit consent for data collection. Advertisers still need to measure campaign performance, optimize spend, and prove ROI, but they can no longer rely on traditional tracking methods. Without a privacy-safe measurement framework, businesses face a choice. Either violate privacy regulations and risk massive fines, or lose measurement capabilities and waste ad spend. The challenge is to enable accurate cross-platform measurement while guaranteeing privacy, ensuring compliance, and maintaining the performance that advertisers expect. This requires fundamentally new approaches to data collection, aggregation, and attribution. Let's walk through the functional requirements. First, the framework must support multiple privacy-preserving measurement techniques. Differential privacy for noise injection, secure multi-party computation for cross-party data analysis, K-Anonymity for user grouping, and tokenization for identity protection. Second, it must provide a unified measurement API that abstracts away the underlying privacy techniques, allowing advertisers to run standard measurement queries without understanding the complexity. Third, it must enforce consent management at every step, ensuring that only users who have opted in are included in measurement, with granular controls for data usage purposes. Fourth, it must support both aggregate reporting and privacy-safe attribution, with configurable privacy budgets and accuracy trade-offs. Fifth, it must provide audit trails and compliance reporting to demonstrate privacy guarantees to regulators and users. These 5 capabilities make the framework both privacy-safe and measurement-effective. Now the non-functional requirements. The framework must be provably private. Mathematical guarantees must hold even with adversarial analysis, not just policy promises. The system must be accurate enough for business decisions. Measurement error should be bounded and predictable, with confidence intervals provided. Performance is critical. Queries must complete in seconds, not minutes, even with billions of events. The system must scale horizontally to handle global measurement workloads across multiple platforms and regions. Compliance must be verifiable. Every data access must be logged, and privacy parameters must be auditable. The framework must be extensible to support new privacy techniques as they emerge. And finally, it must be highly available because measurement is mission-critical for advertisers who make real-time budget decisions based on the results. Here is the high-level system architecture. On the left, client-side SDKs and web pixels collect events with built-in privacy controls, applying local differential privacy noise and tokenization before sending data. These privacy-enhanced events flow through an API gateway into a secure ingestion layer. A consent validation service ensures all events have proper user consent before processing. The measurement engine supports multiple privacy backends, a differential privacy processor for aggregate queries, an MPC coordinator for cross-party computation, and a K-Anonymity service for user grouping. A privacy budget manager tracks and enforces privacy parameters across all queries. The query abstraction layer provides a unified SQL-like interface that automatically routes queries to the appropriate privacy backend. The results service applies final privacy checks and returns measurement results with accuracy bounds. An audit service logs all operations for compliance verification. The key metrics to memorize: cold. Privacy budget utilization, which tracks how much of the allowed privacy loss has been consumed. Measurement error bounds, typically expressed as confidence intervals or relative error percentages. Query latency, the time from request to response, which should be under 5 seconds for most queries. Consent coverage rate, the percentage of users who have opted into measurement. Data utility score, which measures how useful the anonymized data remains for business decisions. Compliance audit score, which tracks adherence to privacy policies and regulations. And cross-platform measurement accuracy, which compares privacy-safe results against ground truth where available. These metrics balance privacy, accuracy, and usability, the 3 pillars of the framework. Let's trace the end-to-end user journey. A performance marketer wants to measure the effectiveness of a cross-platform campaign while respecting user privacy. She accesses the Privacy Safe Measurement Framework dashboard and defines her measurement query. Total conversions by campaign with demographic breakdowns, with a maximum relative error of 5%. The system checks her privacy budget and available consent coverage. The query router determines that this requires differential privacy for demographic breakdowns and K-Anonymity for user grouping. The MPC coordinator coordinates with the partner platforms to compute cross-platform attribution without sharing raw data. The differential privacy processor adds calibrated noise to ensure individual privacy. The results service returns the measurement with confidence intervals and privacy guarantees. She sees that campaign drove 20,000 conversions with a ±3% margin of error, and she can confidently optimize her spend knowing both the results and their privacy implications. The core models and algorithms. Differential privacy adds calibrated noise to query results, with the noise magnitude determined by the privacy budget epsilon. Secure multi-party computation enables multiple parties to jointly compute functions without revealing their private inputs, using protocols like Yao's garbled circuits or secret sharing. K-Anonymity groups users into clusters of at least K individuals, preventing re-identification through rare attribute combinations. Tokenization replaces sensitive identifiers with reversible tokens, enabling deduplication without exposing raw identities. The Privacy Budget Manager tracks cumulative privacy loss across all queries, preventing privacy budget exhaustion. The consent engine enforces granular user preferences, with opt-out mechanisms and data purpose restrictions. The key trade-off is the privacy utility frontier. Stronger privacy guarantees reduce measurement accuracy, so the system must optimize within business constraints while maintaining mathematical privacy guarantees. Now the low-level design deep dive. The differential privacy processor implements algorithms like Laplace mechanism for numeric queries and exponential mechanism for categorical queries. The MPC coordinator uses a mix of garbled circuits for simple computations and secret sharing for complex aggregations, with performance optimizations like circuit cutting and pre-processing. The K-Anonymity service uses generalization hierarchies and suppression strategies to achieve K-Anonymity while maximizing data utility. The tokenization service uses deterministic encryption with per-customer keys, enabling cross-platform deduplication without exposing raw identifiers. The query optimizer analyzes query patterns and selects the optimal combination of privacy techniques to minimize error while respecting constraints. The audit service implements immutable logging using append-only storage with cryptographic signatures, ensuring that all privacy operations can be verified. The system supports hot-swappable privacy algorithms, allowing new techniques to be added without changing the client interface. Key takeaways for your interview. First, privacy-safe measurement is not just about anonymization. It's about mathematical guarantees through techniques like differential privacy, MPC, and K-Anonymity, so emphasize the specific algorithms and their properties. Second, always discuss the privacy budget as a scarce resource that must be carefully managed across all queries. Third, measurement accuracy and privacy are fundamentally at odds, so be ready to discuss how you optimize the privacy utility frontier. Fourth, consent management is not optional. It's a core component that must be enforced at every layer of the system. Fifth, auditability and compliance verification are as important as the measurement itself, so mention immutable logging and privacy parameter tracking. If you can walk through this system with these 5 points, you will signal strong senior-level design thinking for privacy-safe systems. That's it for the privacy-safe measurement framework. If this helped, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on the privacy-safe measurement framework. We covered the full picture, from differential privacy and secure MPC, through consent management, privacy budgets, audit trails, and the low-level design of privacy algorithms and compliance verification. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.